start experiment 14, okay? So experiment 12, and this is kind of, and 13 as well. Experiment 12, last week we talked about the reaction and then monitoring the reaction with TLC, and that's what you guys did in lab. You used TLC at multiple points along the reaction to check how things were going. When you see a single spot on a TLC plate, what does that tell you? What does that single spot on a TLC plate tell you? Like if you have a lane and it has one single spot, what does that tell you about that, whatever you spotted on that lane?
Pure by TLC.
It's pure by TLC, right? And remember that disclaimer, okay? Because if you can't see it with the method of visualization you're using for the TLC, you can't necessarily say it's 100% pure, but it is pure by TLC, okay? And so in our case, we only can see things that are UV active by TLC. So just keep that in mind when you're saying things are pure by TLC. The other thing is how you spot things will kind of change how things, RF values of things, or how, if the chamber wasn't perfectly still and you jostled it around, it'll move things around a little bit. So those kind of things will change RF values. But if your RF value is a little bit lower of one spot versus something else, it's not like a melting point that you can say, it's depressed because it's not pure. If you see one spot, it is pure by TLC, all right? So don't try and intermix. I've had students before try and intermix TLC and melting point concepts, and they don't intermix, all right? So is everyone clear on that one? Okay. That was the big one I wanted to point out for experiment 12. All right, experiment 14. We, again, are going to talk about something you haven't talked about in lecture before. And so here we go. But the good news is you'll have it now, and then you also have it in lecture. So you'll get it twice. So we're going to do a Friedel-Crafts Alkylation. That means that this type of reaction occurs on aromatic rings. That means we're actually going to use aromatic rings as what we are reacting on, okay? So up till this point in lecture, you've pretty much been told, and in lab, we've stayed away from any reactions occurring on the aromatic rings. We're now actually going to get a reaction to occur on the aromatic ring. But it takes some pretty specific conditions, okay? So in this reaction, you're going to get alkylation of the aromatic ring. And that happens there's going to be multiple ways that you learn how to do reactions on aromatic rings. One of the ways is electrophilic aromatic substitution. And in lecture, they will break down all of this information, okay? So we are looking at electrophilic aromatic substitution. And so what that means is we are going to substitute something on the aromatic ring with an electrophile. In our case, we're substituting, and usually what you're talking about is you're substituting a proton with another group on that aromatic ring, and we're going to do it with an electrophile. Now, what happens is the aromatic ring acts as the nucleophile because it's got all that electron density in the ring, all right? But it's not a super great reactive nucleophile unless you've got just the right situation. So we've got the aromatic ring is our nucleophile in this case, but you need a really strong electrophile. So it won't just react with any old electrophile. You have to have something that is a really strong one. So we are going to make carbocations, which are really, really great electrophiles, okay? And so what happens is, in general, we've got this aromatic thing. We're going to react it with an alkyl halide. And we're going to use a Lewis acid. That helps us prepare that carbocation, prepare our electrophile. And then in the process, we get the R group from our alkyl halide to add on to our aromatic ring, okay? And so La is our Lewis acid. And that is going to help prepare that electrophile. In our case, we're going to use aluminum chloride as our Lewis acid, okay? And so we'll go through here kind of, I'm going to put this up here, and then I'm also going to talk through it on the board, okay? What happens before you can have the reaction at the aromatic ring is you have to have the Lewis acid react with your alkyl halide to make that carbocation. And so what's happening, I'm going to use the example of 2-chloropropane. So we've got chloropropane reacting with our aluminum chloride, and eventually we're going to form this carbocation, but kind of in between, what happens is we've got this partial positive charge here on our carbon that chlorine came from, and that chlorine is kind of partially associated with this carbon, and it's partially associated with the aluminum chloride. And so then in the end, we get this carbocation, and then in this case we get aluminum tetrachloride, and that has a negative charge on it, okay? So there's this kind of in between here, where we've got this chlorine that's kind of between our chloropropane and in between the aluminum chloride. We eventually get to the point where the chlorine goes with the aluminum chloride, and we form, this is our electrophile, there's our carbocation, okay? And so then, that carbocation, then we've got our carbocation here. It can react with our aromatic ring. We've got our electron density that's going to, so remember the way we draw mechanism arrows, the density is going from the aromatic ring to our carbocation. And so then we get this carbocation that then is attached to our aromatic ring. We've got now our positive charge has to move, so now it's on the ring itself. And from here, we can draw multiple resonance structures of how that carbocation moves around the ring, okay? So we've got it here, and we've got it here. So we've got 3 different resonance structures, all right? Then eventually, that aluminum tetrachloride helps take our proton here, we re-aromatize, and then we get HCl and aluminum chloride. So we regenerate our aluminum chloride, so what do we call that as far as our reaction is going? That is a catalyst, so it's a Lewis acid catalyst, okay? And we also give off HCl in the process, okay? So we're going to talk about how we're going to take care of that with our reaction, because we do give off HCl. We re-aromatize, and now we've got the alkylation. So this is the alkylation part. We've added that alkyl group to that aromatic ring, all right? And we're we're able to form our resonance structures here and our carbocation here on our aromatic ring, and then the driving force to get to the product is we're going to reform this aromatic ring, so it wants to push it towards that product, okay? Or push it towards an aromatic product, all right? So this is just with benzene and 2-chloro-propane. We are going to use something a little bit better. We're going to use toluene, okay? And so our aromatic ring is going to be the toluene. The reason for this, and you're going to go through all of these tables when you talk about aromatic substitutions in the lecture, okay? The piece that is important to us is this part here of this table, which is in McMurray, all right? You're going to talk about all of these different substituents, meta-directing deactivators, ortho and para-directing deactivators, and then ortho and para-directing activators. And what makes them activating is they can add a little bit of electron density to that aromatic ring to help stabilize the fact that you actually are making a carbocation on the aromatic ring, okay? And so one of those is the methyl group. So toluene, remember that toluene is this guy. So it has the methyl group right there on the aromatic ring, okay? And so we're going to take advantage of the fact that that methyl group is there, and it's an ortho-para directing activator because it can add a little electron density to the ring, okay? And it's not like an electron, we're just talking about electron density, okay? So we're not saying it's going to donate a whole charge to the ring, we're just, it can stabilize it with a little bit of electron density that it can contribute to the ring. So for right now, don't worry about the rest of these as far as our reaction is concerned. This is what is important for what we're doing in lab this week, okay? But like I said, they're going to go through and lecture all of this information, all right? So we're going to look at the reaction we're doing, and then we're going to talk about the different possibilities of what can happen with our reaction, okay? So we are reacting with, we're taking toluene, all right? So everybody will be starting with toluene. And you're going to react your toluene with either 1-bromo-propane. So some of you, this should be familiar because this is what you used in the Grignard reaction. It's still the same 1-bromo-propane. Or you're potentially reacting with 2-bromo-propane. Okay? And we will, when you come to lab this week, we will tell you, unless your lab prof tells you ahead of time, we will tell you which alkyl bromide you're going to be using, okay? So in your pre-lab, you're going to want information for both of them, all right? But it's important to have that information because in the end, you're going to compare all of the data that we're going to talk about for possibilities of reactions here. In both cases, we're using aluminum chloride as our Lewis acid catalyst, all right? Now, there's different possible products, okay? And so you guys have not talked about, I don't think you've talked about the names of substitutions around an aromatic ring, like ortho-meta-para. Okay, well, we'll go through that here. All right. So we've got our methyl group. And in theory, we can add an alkyl group in relationship to that methyl group anywhere around the ring, all right? If we add it either here or we added it here, this is called the ortho position relative to the substituent, okay? The 1-2 position is the ortho position, all right? So this is ortho. And this position and this position are equivalent. Do you see that? Like there's no difference between here or here. They're both ortho, okay? We're both looking at mono substitution though, so I'm not going to draw it on both sides, all right? So that is the ortho substitution if we add 1 bromopropane, all right? This here is what we would add if we added 1 bromopropane. Does everyone see that part? Okay. If we added 2 bromopropane, and again we're looking at ortho substitution, that's what would be added from 2 bromopropane, because you're adding at this carbon, okay? And that's that carbon there. So this would be our 2 bromo product, okay? We can also add directly across from the methyl group. So here, this is called para substitution, this 1,4 substitution, okay? Para is 1,4, all right? So if we're talking about the 2 bromo products, that is our para substitution, okay, from the 2 bromo. Everyone good there? Okay, the last one is meta substitution. So that would be here. Either here or here. Either side is equivalent, okay? Meta is 1,3 substitution. So 1,3, okay? So then here, with the 2 bromo, that would be our substitution. 1,3. And just like we talked about with ortho, it could be in this position or it could be in this position, but we're talking about mono substitution, so I'm not going to show it on both sides. So this is the different way that the alkyl groups can be substituted on the aromatic ring, and these are the names for those types of substitutions, all right? In your lab manual, in your textbook, it's going to talk about orthopara being a kinetic situation, and it's going to talk about meta being a thermodynamic situation, okay? And we're going to try and actually break that down in the experiment that we're looking at, okay? So when we talk about kinetic products, if you go back to Gen Chem, what do you remember about kinetic versus thermodynamic? What would form like most instantly, kinetic or thermodynamic? Kinetic, right? They were the products that would form first, so that meant they're getting to the products, that energy barrier was the smallest. These kinetic products would form first. Thermodynamic products, it would equilibrate to those, right? And usually what that would mean is that would be the most stable product would be the thermodynamic product. If it could equilibrate there, it would go to the most stable product, okay? So kinetic would be most quickly formed, most easily formed. Thermodynamic would be the most stable product, what it would equilibrate to, okay? And so we're going to look at those concepts, kinetic versus thermodynamic, and what you guys do with the experiment this week, okay? The other piece of this is if you consider the carbocations, which is going to be the more stable carbocation? One from the 1 bromo or the 2 bromo? 2 bromo is going to make the most stable carbocation, right? Because it's going to be the secondary carbocation. So we're also going to look at another piece that involves the carbocation, all right? And so one bromopropane can form either this, which would be the direct formation of the carbocation, okay, or it can equilibrate to a more stable carbocation. Okay? And so this can happen, and then you get whatever carbocation is present to add to the aromatic ring. Okay? And so what this means is when you're using one bromopropane, you could see either these products or these products because of that carbocation rearrangement that's possible. Okay? So with this, we're looking at a carbocation rearrangement. Okay. If you look at one bromopropane reacting, and you think in terms of kinetic versus thermodynamic, what would this carbocation be? Kinetic, because it would be the first formed, right? Okay. And in equilibrating to this would be the thermodynamic carbocation, because this would be the most stable, but it's not going to be what's first formed. Okay. So that's another piece that you're going to look at. Does the carbocation, not only what products do you get, but also what is going to happen as far as the carbocation rearrangement, okay? And what do you get as a result of that versus just the substitution, okay? So with that, well, let's consider our possible conditions, and then we're going to talk about why all this is possible. Okay, so in your textbook, it talks about different conditions, or sorry, textbook, lab manual. It talks about different reaction conditions. Okay, and it's important that you keep those like what you label in your notebook and what you label for your experiment needs to stay consistent with the lab manual, okay? So when we're talking about different conditions, A, B, C, and D, these are the conditions that we're talking about, all right? So for A, we're going to do this reaction at 0 degrees, our reaction of toluene with your bromopropane, and you're going to do it with one bromopropane, all right? And so because of that, the possible substitutions you could get are adding propane to the aromatic rings, or you could get isopropane, or the isopropyl group to add to it. Does everyone see that? Because you're starting with one bromopropane, you could end up with just propane added or isopropyl group added. Okay? For B conditions, we're going to do this at reflux, and we'll talk about here in a minute how we do that. Okay? With one bromopropane. So what kind of products would we get? One bromopropane. We'll get the propyls, right? And then also the isopropyls, right? Possibly, because of the rearrangement. Okay, so A is 0 degrees, 1 bromopropane. B is reflux with 1 bromopropane. C is 0 degrees, but now we're going to use 2 bromopropane, okay? So what products do we expect with that? Just the isopropyl, right? You don't really expect it to go backwards, right? So this is what you're expecting with the 2-bromopropane, right? And D is reflux. And so with 2-bromopropane, so again, we just expect the isopropyl products. Everyone good there? Okay. So these are the different conditions we're going to use. So what that means is we're not going to have everybody run 4 reactions this week. Everybody will be responsible for one set of reaction conditions. So that's what we're going to assign to you in lab. We'll tell you what set of conditions. We'll give you the letter of what set of conditions you're going to run. And then you're going to do that for a group of 4, including yourself. So when we go to the data comparison part, we're going to have a group of A, B, C, and D data that all of you are looking at. And that is going to come from the different members of your group, okay? So you're doing one reaction, but you're a member of 4 people's data, including yourself, okay? So be really careful when you're doing it, because not only does your data count on it, but 3 other people are counting on what you're doing with your reaction, all right? Now something to look at here, and you guys will look at this in more detail when you guys talk about the mechanisms and different substituents and so forth in lecture, okay? But for our particular reaction, okay, and this is drawn in the case of the isopropyl carbocation, but it works just the same with the propyl carbocation, okay? We've got we've got toluene that we're reacting, okay? And it has that methyl group on it. And remember, it's an ortho-para directing activator. It's got a little bit of electron density that it can push towards that aromatic ring, okay? When we're reacting with the carbocation that's generated, this is the initial, like if we're looking at ortho substitution, this is the initial types of substitution we're looking at, okay? And so then we get a carbocation here. But then from resonance, these are the other possible resonance forms that can be drawn from this carbocation, okay? So the movement, we get electrons moving, we get this carbocation form, we get electrons moving here, we get this carbocation form, okay? Same thing, meta. If we add meta, here's the meta position. We've got a carbocation form. We draw resonance structures and move the electrons around the ring. Then we can form this structure, okay? Same with para substitution. Para from that methyl group is here. We form this carbocation. We can show the resonance structure for this carbocation and then the resonance structure for this carbocation. All right? Everyone good so far? Okay. So the methyl group gives us some electron density. Between ortho and para, what do you see in common in relation to that methyl group? Anything in common? Like where that carbocation might be in one of the resonance structures?
To another structure where the positive
So it's on the carbon. You can draw a resonance structure where it's on the carbon of the methyl group, okay? So then you've got a tertiary carbocation. That's going to be more stable than anything that we could show for meta, right? Because all of these are going to be secondary carbocations, okay? But we've got a resonance structure that shows it as a tertiary carbocation for ortho and para. That is what contributes to saying that the ortho and para are going to be the kinetic products, okay? Because they have this extra piece where you've got a resonance structure for a tertiary carbocation, okay? Versus meta does not. So this energy barrier is going to be a little bit less than the meta's energy barrier. All right? Everyone see that? And so that's where the kinetic versus thermodynamic comes into play. And then we also have the piece like we talked about with the carbocation rearrangement coming into play of what adds on here, what you start with and what can actually add there. Okay? So those are the two pieces that we're going to end up looking at with this data analysis. Where the substitution occurs and what carbocation added to form the product. All right? Okay. For this reaction, what gas did I say was generated from the reaction? HCl is generated, okay? We have to account for that in what we set up because of the HCl that's generated, all right? So you each are going to be doing your reactions in a filtering flask, okay? So not a round bottom flask, but a filtering flask, all right? And you're going to do it with, like, you want to make sure that you're flat on your stir plate when you're setting things up, okay? The people that are starting at 0 degrees are going to set this up in their pan. The people that are starting at reflux are going to set this up directly on your hot plate, okay? So you want to make sure with the Erlenmeyer flask, it's a little bit different than the round bottom flask. It needs to sit directly flat on the hot plate or you're going to have trouble with the stirring, okay? With the people that are doing the reaction at reflux, you won't start actually heating till you've added all your aluminum chloride. So make sure you follow the directions in your lab manual very carefully. It tells you when you're going to start heating. You don't start heating till you've added all that aluminum chloride. For the people that are doing the reaction at 0 degrees, you're going to start in an ice bath, okay, and then stay there, okay? So you will set your reaction up in your pan, make sure everything's nice and flat, and then put ice around it. So I wouldn't take your pan of ice, try and put your Erlenmeyer in it. It's not going to sit nice and flat. You want to put the pan under the Erlenmeyer, then use another container to put the ice around in your Erlenmeyer flask, okay? Because of the HCl gas that is generated, we're using the filtering flask to help then have a way that we get rid of that HCl gas, okay? So this is what we're going to call our trap for that HCl gas. So we've got a hose going from our filtering flask. It's going to be clamped up here. We also want to put a little dip in it here, and then go down into a funnel that's sitting in a beaker of water, and you're going to have it so the lip of the funnel is just barely under the water. That way what happens is as the HCl is generated, it goes through the tubing into this funnel and then is trapped in the water, okay? So as the reaction goes, you're going to actually see bubbles being puffs kind of going in that water. That's the HCl that's being generated going into the water, okay? So it's HCl and HBr because we're using the bromopropanes, okay? You put this little dip in your tubing, so we've got a setup in each lab to show you this, because what can happen is you get stuff flowing this direction in the rubber tubing, but you can also get it going backwards in the rubber tubing, and you're going to analyze this reaction with GC just like you did with experiment 8 and 11. If you get any of this rubber tubing going back into your reaction, you're going to see it in your GC. Your GC will be the one that'll be like a million peaks because you'll be analyzing all of that black tubing as well, okay? So you want to prevent any of that from going backwards into your reaction. So that's why there's this dip in the tube here, and you can even use a clamp to hold it, and then we're going to have a clamp up here to hold the tubing, and then we want a clamp on the funnel to hold the trap, okay? And then you just have a rubber stopper in the top of your filtering flask. Because you are generating an acid gas as this reaction is going, don't set it up like right next to the front of the hood. Set it up towards the back of the hood, okay? So then the acid that's being generated, whatever is trapped in the water, is going towards the back of the hood, not flowing right at you, okay? And then when you're, as you're doing the reaction, whenever you don't need to be in the hood, keep the hood sash closed, okay? The aluminum chloride is very moisture sensitive, okay? So it reacts really well with water. So first of all, in setting things up, you want to make sure that your apparatus is really dry. Make sure your flask is dry, no water present. Make sure, like, shake out the tubing really well, dry out the tubing, make sure there's no water present in the tubing either, okay? Now, aluminum chloride reacts with water. Where do you have kind of exposed moisture within your own body? Mouth or eyes, right? Or your nose, okay? And so if you get any dust, like inhale any dust or get any in your eyes, it's going to react with the moisture that is there, okay? And what it does is just like when it's reacting with just regular water, it's going to form HCl as it does that, okay? So you don't want, you don't want it in your eyes or your nose or in your mouth. So be really careful with it. Make sure you've got your safety glasses on. Make sure you have your gloves on. Make sure you handle it in the hood, okay? We have already weighed out the aluminum chloride for you in vials, so you don't even have to weigh it out, all right? So what you're going to do is you're going to get a vial of aluminum chloride. You're going to weigh the vial, the cap, and the aluminum chloride. And then after you add it to your reaction and you're all done, you're going to weigh the vial and the cap again, okay? That way, you don't have to deal with transferring the aluminum chloride at all outside the hood. It's all going to happen in the hood, all right? But make sure you wear gloves when you handle it and keep it in the hood because you don't want any of that dust coming in contact with you, all right? So you have to be really careful because it's moisture sensitive and it can react with the moisture that you have present in your own body. So keep it in the hood, wear gloves, don't inhale the dust, okay? Only weigh the full vial before you uncap anything and weigh the empty vial after it's completely empty, all right? Now your lab manual is going to tell you how to add that aluminum chloride, okay? You're going to add it in portions. You are not going to add it all at once. You add it all at once, you're going to get a really hot reaction, okay? Because that aluminum chloride wants to react with that alkyl bromide very quickly, okay? So you want to add it in portions, follow the instructions in your lab manual for how you're going to add it in portions, all right? But you're adding in portions. Then after you've added in portions, let it react for a few minutes, okay? And then you're going to let it, if you're in an ice bath, just let it stir in that ice bath for a period of time. If you're going to heat it, you're going to heat it for a period of time. Our flask here is going to be kind of all of our reflux apparatus, okay? So we've got our flask. This part of the Erlenmeyer is going to be basically our condenser, okay? And then we're going to make sure that we don't go beyond our flask and go out into the tubing and get that to come back in, okay? So you want to heat it really gently. On your hot plate, like one or two, okay, because it's sitting directly on the hot plate. And you don't want vapor going beyond, here's our condenser area, we're going to put a wet paper towel around there to help with it condensing. You don't want it going beyond that. You don't want to see any vapor going into your black tubing. Otherwise, you're heating it too high, and you're going to end up with potentially getting black tubing gunk back into your reaction mixture, okay? All right. So be really, really careful with the heating, okay? As far as then the vial of the aluminum chloride, okay, that empty vial, it reacts really well with water, right? Once you have weighed that empty vial and cap, you can take a beaker of water and submerge the vial and cap into the water, okay? And that will finish off the aluminum chloride. It won't be reactive anymore. So you just, with gloves, probably use your spatula to push it down in there. Put the vial and cap in a beaker of water. It'll kind of make a little gas and hiss a little bit, and then you'll have killed all that aluminum chloride. There won't be anything left, all right? And then you can clean out that vial just like you normally would, okay? Clean it out with soap and water, rinse it well with water, rinse it well with acetone, and you can put it in the extra vial containers, okay? Then at the end of your reaction, you're then going to have to also quench the reaction, okay? So when you're done with your stirring in an ice bath or done with your stirring while it's heated, you're going to make sure everything, if your heating comes down to room temperature, if you're in an ice bath, I just leave it in the ice bath. Leave your acid trap connected, okay? Because the next thing you're going to do is quench that reaction with an HCl acid solution, okay? And so it's going to generate even more, whatever aluminum chloride is left, it's going to generate more acid. So leave that acid trap connected and carefully quench the reaction with the HCl solution. You're going to prepare that from 12 molar HCl, okay? So you've got concentrated HCl, and then you're going to use that to prepare this solution. Be careful handling the concentrated HCl. Use gloves, don't spill it. If any is spilled, let us know so we can clean it up right away, okay? Then once you're done quenching the reaction, you're gonna have two layers. You'll have your toluene layer and your aqueous layer. You're going to put things in your separatory funnel, separate your layers, okay? And then you're going to wash your toluene mixture with water to make sure you've got all the aluminum chloride, all the acid away from it, all right? If in the first separation you have trouble separating the layers, it tells you can use sodium chloride to help with that separation. If you have trouble separating the layers when you go to do the wash with water, just be kind of careful. You want to mix the layers, but don't shake them really vigorously because you're probably going to have trouble with the separation again, okay? And so if you have to use sodium chloride solution in the first separation, you're probably going to need it in your second separation, all right? And what ends up happening is you kind of get layers that look like kind of like, I don't know if you guys have seen lava lamps, where you've got like mixture of layers, and they kind of just want to like be globs of mixture together and not separate into two nice distinct layers, okay? And so if you end up getting that, then we're going to use sodium chloride to try and help that out. But when you do the wash with water, make sure you use the sodium chloride instead of just water for that, okay? Then you're going to dry the organic layer. So what will we use to dry the organic layer? Magnesium sulfate, right? And you don't want to have to rinse this layer with toluene. You're trying to look at the overall composition of what that mixture is with the GC. Your toluene is your solvent, but it's also your reactant, and you don't want to change the relative percentage of what is in there, okay? So with the magnesium sulfate, just like with experiment 11, only use what you need to dry it. So a little bit, you should have some clumping with a little bit of free floating. After you've added that, that's plenty. Cover it with saran wrap, give it a good stir, let it sit for 10 minutes, and then you're gonna filter the mixture with gravity without rinsing it. So just like the alkene, you didn't want to rinse it with anything, you're not going to rinse this mixture with any toluene. You don't want to change the toluene composition, okay? Then what you're going to do is you're going to get a yield of that toluene mixture. And then after you get your GC data, you're going to go back and figure out how much of it is actually alkylated toluene. And you'll take that percentage times this yield and figure out how much product you made, okay? So you want the yield of the whole mixture, toluene and everything, after you dry with magnesium sulfate and after you filtered it. Get the yield of your reaction mixture, okay? And then the other piece is you're going to prepare a GC sample. And so just like 2 weeks ago, you're going to look at your mixture, make sure there's no solids or evidence of water. You can take a drop of that sample, put it into a clean dried GC vial, fill it to the neck with pentane and cap it, and then you'll submit your sample just like you submitted your GC samples a couple weeks ago in the sample tray, and then fill out your information on the sample sheet. And remember, use initials and notebook pages for that, okay? Hang on just a sec. Yep.
So in the Prelab, do you need to put a flow chart for each A, B, C, and D?
The flow chart is pretty much the same. It's just because what you show in the flow chart is just what happens after the reaction, okay? So you don't have to show the heating part or whether it was cold. You're showing what happens after the reaction and what you do afterwards. And what you do afterwards is the same for both, okay? One thing I'm going to give you guys, though, real quick, that's why I said hang on. I am going to, so I told you have to have the information for 1 bromopropane and 2 bromopropane in your Prelab. I'm going to give that to you right now, okay? So 1 bromopropane, its molecular weight is 123 grams per mole. Its density is 1.353 grams per milliliter. And its boiling point is 71 degrees. Okay? 2 bromopropane, its molecular weight is going to be the same thing, right? Because it's just an isomer, 123 grams per mole. Its density is 1.31 grams per milliliter. And its boiling point is 59.4 degrees C. So now you have that information for the 2, the bromopropanes, okay? And that would be the extra information that you need in your lab manual or in your lab notebook besides figuring out amounts, all right?